We'll get started in about 2 minutes, though. I think you can all see the warm-up, right? Is it on the correct screen share? No? Yes? Is anybody out there, or did I mess up my classroom settings?
No, we can see it. Sorry. Just something happened.
Okay. Anyway, I got 3 matrices here, matrix A, a matrix B, and a matrix C. And what I would like you to do is I would like y'all to do this 5-part warm-up. I would like the product of BA, AB, BC, CB, and CA. Now, does this warm-up actually have 5 parts?
Mr. Robinson.
Welcome. Does this warm-up question actually have 5 parts?
No.
Is every single matrix product possible?
No, not all of them are possible.
Yeah, not all of them are possible. So before you do this, what I would recommend doing is go through and write down the dimensionality of matrix A and matrix B and matrix C, and then compare that down below to what I'm asking you to do in parts 1 through 5. Figure out first which ones of them are possible and which ones of them are not possible so that you don't run into any issues. Though if you were to try and multiply 2 matrices, and keep in mind when we multiply matrices, we take the row of the first matrix and the column of the second matrix. If you were to try and do that with 2 matrices that had the wrong size dimensionality, you would very quickly figure out that what you were doing wasn't possible. Also, one of these 2 will be relatively time consuming.
Hey, Mr. Robinson.
Good morning. Okay, let me take attendance and then we'll get started. How's it going out there?
We're all right.
Bad now.
Bad now?
Yeah.
Why?
Yeah, why is that?
Chris, check teachers real quick,
Wait, what?
and you'll see what I mean.
I know you're not talking about my grades. I haven't
No,
graded
not
anything
your
in
class.
forever.
No,
Oh,
nothing for
okay.
your class.
Okay, let's go ahead and get started. Especially since we also have a notes to do today. Sorry, one person just came in late. Let me add the attendance. Okay. So let's go ahead and start off by listing out the dimensionalities for each one of these so that we can try and figure out what to expect in terms of the outcomes of these products. What's the dimensionality of matrix A that I invented here?
2 by 2.
That's a 2 by 2. And then what about matrix B?
2 by 3.
And then matrix C here, that's a 3 by 3. Yeah?
Yeah.
So I'm going to go ahead and I'm going to go down below real quick and I'm going to list out my dimensionalities. So this is a 2 by 3 and a 2 by 2. This is a 2 by 2 and a 2 by 3. This is a 2 by 3 and a 3 by 3. This is a 3 by 3 and a 2 by 3. And then down here at the end, this is a 3 by 3 and a 2 by 2. So what's the condition that we're looking for to see whether or not these matrices have products? What's the rule that we have to enforce?
The numbers in the middle have to be equal.
15 seconds.
Yeah, and that's why I like this
Pretty much.
technique, because it doesn't like get too into the weeds in terms of vocab. We are checking to see if the middle two digits are identical, and then that lets us know that we would get a matrix of the outside number dimensions, right? Technically, what we're doing is we're checking to see the number of columns of the first matrix, and we're comparing that to the number of rows of the second matrix to see if they're identical. But this is a real quick and easy check that shows that item 1 here has no product because this is 3 and this is 2. So no product. Matrix 2 can be, I'm sorry, product 2 is doable, 2 and 2 agree. Product 3 is doable because 3 and 3 agree. Product 4 is not possible because 3 and 2 do not agree. So there is no product there for item number 4. And then for item number 5, 3 and 2 do not agree. So again, there is no product. So there's only actually 2 products to take here. Are there any questions on that first part, the filtering out of impossible questions? No? Okay. So let's go ahead and get into it. First, we'll do item number 1 here, matrix A multiplied then by matrix B. So for AB, we're going to say that this is equal to 2, 6, 3, 0. And we're going to take that and we're going to hit it against matrix B, which is 6, 4, 1, 0, 2, 3. And, you know, whether or not you're actually highlighting this stuff is up to you, but I just think it makes it a little bit more visual. So if you have colors on hand, you might as well use them. Keep in mind that it's always the rows of the first matrix being multiplied by the columns of the second matrix. What we're checking for is to make sure that this line is the same length as this line. That's what you're actually doing when you are checking to see that this number and this number are identical. Nonetheless, this is going to give us a matrix of products, and for each one of these entries, keep in mind that we are multiplying and adding these terms together. So this first entry is going to be 2 times 6 plus 6 times 0, which is 12. And then it's going to be 2 times 4 plus 6 times 2. So that next entry is going to be 8 plus 12. Oh, and I guess I should do it the same for all these. So this first entry is actually 12 plus 0. Yeah, just for the sake of having some visual symmetry here. And then it's going to be 2 times 1 plus 6 times 3. And that deals with row 1. And now to build out row 2, it's going to be 3 times 6 plus 0 times 0. And then it's going to be 3 times 4 plus 0 times 2. And then finally, for our last entry here, it's going to be 3 times 1 plus 0 times 3. And so when we're done, we go through and we add up all of these entries, and we should get 12, 20, 20, 18, 12, and 3. Are there any questions about the product of AB?
No, looks clear.
Yeah, looks good. Okay. And then the other one that we can take a product of is going to be BC. And notice here on the inside, 3 and 3, those are identical, that checks. And so the outcome matrix from this that we're going to get is going to be a 2 by 3, which I think is kind of interesting that you get that same result, even though these matrices are larger than these matrices. A 2 by 2 multiplied by a 2 by 3 yields a 2 by 3. So we got down here. Up here, BC is a 2 by 3 and a 3 by 3, and even though that second matrix is bigger, the size of the product is exactly the same. It's just that what we have to do to make the terms inside of it is going to be a little bit more complicated, which is why I built in these additional zeros into C so that it would be easier to take that product. Nonetheless, we're going to do B times C here. So BC is going to be equal to 6, 4, 1, 0, 2, 3. And then matrix C is going to be 6, 0, 3, 0, 2, 1, 5, 0, negative 2. And again, since I have access, oh, and there's a College Board highlighter. It's free from a conference. Rows by columns. Oh, by the way, have you all heard about the updates to the SAT or whatever? Should I talk about that real quick? Did I give an SAT update yesterday?
Yeah, but didn't they release something like
Yeah, they sent out
yesterday?
an email. Yeah.
Oh, okay. I'll have more information Friday because they're going to do like a webinar on Friday for people who run counseling departments, and my wife has to watch it, so I'm going to watch it to pick up extra information anyway. But yeah, they don't plan on bringing it back until I think their tentative plan right now is July, but it's probably going to get pushed later than that. And when it comes back, they're going to offer it weekly instead of once a month, so that like everybody who wants to take it once it comes back has that opportunity. But most major universities have waived it for this year, so not having it probably won't hurt against you. But if you do have it and you have a good score, that will definitely add value to your application. So you know, if you're doing prep still or whatever, that's worth doing. And if you're doing SAT prep and you ever want to just like hang out and talk about the math questions or whatever, shoot me an email and we'll set up like a personal appointment to do a Zoom thing'em. And then you can just email me the questions you have and I'll solve them out here. Is that cool? Yeah, that's cool, Mr. Rob. Okay.
Yeah, thanks, Mr.
Yeah, for sure. Yeah, and hey, it's free, man. I charge pretty steep rates. So nonetheless, our product matrix here is going to be made of all of these entries. And like I said, even though the final matrix in the end is going to be the same size, what we have to do to generate the terms inside of it is going to be more complicated. Simply because this does produce 2 by 3 in the end, yeah? But each one of these terms is made of 2 numbers. What's the deal here? It's still going to produce 6 digits in the end, but each one of the digits is going to be made out of, instead of 2 numbers,
3.
each one of these is going to be made out of 3 numbers instead. So to get entry 1, 1, we're going to take row 1 and multiply it by column 1. That'll give us entry 1, 1 of our new product matrix. But this is going to be 36 plus 0 plus 5. Again, that's 6 times 6, 4 times 0, and 1 times 5, giving me the sum of these 3 digits. And then I'll move across to get that next one. So that's going to be 0 plus 8 plus 0. And then we'll move across to this final entry here, and that's going to be 18 plus 4 minus 2. And then down below, we'll do the same thing, row by column. So that's going to be 0 plus 0 plus 15. And then this next entry is going to be 0 plus 4 plus 0. And then this final entry is going to be 0 plus 2 minus 6. And then again, after we have the set of terms that we have to sum for each one of these positions, simplify it down, and that'll be our final product matrix. So this one is going to be 41, 8, 20, 15, 4, and negative 4. Are there any questions on the product BC? Ooh. No? Let me update attendance one more time and then we'll get into notes for today. Before we do the notes for today, are there any questions on the homework for the previous section, which is due tonight? Pretty easy stuff, right?
Yeah, it's simple.
Yep. In a lot of ways, today is more of the same. I think today's stuff is pretty easy to hold on to and do, so long as you've been keeping up with the rest of the stuff that we've been doing in the class. All that we're actually doing today is we're going to pick up a little bit of new vocabulary, and we're going to learn a new way to solve the systems of linear equations that we were solving for the whole first half of this chapter that we solved out on the mid-chapter quiz right before break. Today we'll be talking about section 9.6. Solving systems by Gaussian elimination. Before we get going though, just because I like to do a little bit of the history instead of just like jumping into it. The dude who this method is named after is a really important mathematician / physicist in history, which is why I like take the time to talk about him. His name was Carl Friedrich Gauss. And he was a 18th century dude. He lived from 1777 to 1855. And this is one of the like easy things he did, relatively easy, was the development of a bunch of these rules of matrix mechanics, which are really important for the development of later physical theories and mathematical methods. But the reason why his name lives on is not just Gaussian elimination, but one of his students who whose name you will again see in a bunch of places as you move forward through math and physics. One of his students whose name was Lagrange, who probably went on to be more important than Gauss in terms of total impact. But then again, like, you know, where would Lagrange have been without having Gauss as a teacher? Lagrange basically codified all of the rules of magnetism. So Lagrange, who is Gauss's student, made the rules of magnetism, which that work was started by Gauss when he was like in his prime. So to kind of honor that legacy and the fact that most of the hard work was done up front by Gauss, Lagrange made these laws of magnetism, but still to this day, we call the laws of magnetism Gauss's laws. You actually see this in a bunch of places in science where like one homie did a thing, but he knew that that development wasn't completely on his own. And so he named it after the person who started the work, not the person who finished it, which is why like one of the most important physical constants is called Planck's constant. But Planck is not the one who calculated the value of that constant. The one who calculated the value of that constant was actually Einstein. He easily could have like walked away and called it Einstein's constant. Nobody would have argued with him, but you know, he gave credit where credit was due. Nonetheless, here's what we're talking about today, and we're actually going to start off with a little bit of talk about something that isn't Gaussian elimination. Let's go ahead and start off with the definition, a little bit of vocab of the identity. I got into a good flow, right? Explaining who this dude was and why we care about him, and I totally neglected the portrait. This is like the most famous painting of Carl Friedrich Gauss. This is the dude who invented this thing. This is also the dude who started the work necessary for us to understand how magnets work. And magnets is what gives us electrical generators, which is what makes possible the modern electrical economy. Y'all see that, right? The portrait? Yeah? Okay, good. So in order to understand why Gaussian elimination works, why it's cool, we must first understand the identity matrix. Now, the identity matrix has the following properties, though it can be of any size, which is why I'm going to define it out formally in the following way. The identity matrix is a square matrix such that, and typically we call the identity matrix capital I, which means that the entries within it would all be lowercase i's. So the identity matrix is a square matrix such that all of its entries, I sub AB, are equal to 0 if A is not equal to B, and all of its entries, oh, I'm sorry, I don't need that second part. Oh, no, I do, okay. And all of its entries, I sub AB, are equal to 1 if A is equal to B. And if you follow these rules, you can generate any sized identity matrix. So let's go ahead and generate a few different identity matrices of dimension 1, of dimension 2, of dimension 3. And I think after you see what the third identity matrix looks like, you'll have a good idea in terms of like what it is exactly the identity matrix is. So if I say that I want an identity matrix of dimension 1, this is to say that I want a matrix that has 1 row and 1 column, right? So the only position in it is that 1 position, 1, 1. And if you look at the definition of the identity matrix here, well, okay, if the identity matrix only has 1 entry, and that's 1 and 1, A is equal to B. So the only value in that identity matrix is the number 1. An identity matrix of dimension 1 is simply the number 1. Let's go ahead and talk about an identity matrix of dimension 2. Identity matrix of dimension 2 is going to be a 2 by 2 matrix because the identity matrix itself is always square. And what is this first position? What is that entry? What position is that inside of this matrix?
1, 1.
1, 1. So again, if A is equal to B, then we're going to say that that value there is equal to 1. What about this next value? What position is this?
1, 2.
This is 1, 2. So this is saying that A is not equal to B because those indices are not exactly the same. So this value is 0. This next entry down here?
2, 1.
0.
It's also 0 because it's the position 2, 1, which means A is not equal to B, so that's a 0. And then we get down here to 2, 2, where these guys are equal again. And so A is equal to B, and we get back a 1. And so I think you can see what the functionality of this definition is. When we're talking about a matrix, and we are talking about these entries being the same, that's talking about the diagonal. Position 1, 1, position 2, 2, position 3, 3. All of those entries are 1 when it comes to generating an identity matrix, and all of the other values are 0. 0, 0, 0, 0, 0, 0. Is this okay in terms of like the formal definition of an identity matrix?
Yeah, pretty good.
And it's important to keep in mind that this definition, the reason why we define it this way, is that it can carry all the way up to an infinitely dimension matrix. It doesn't matter, you could generate as big of an identity matrix as you want. It can have as many entries as you want. The diagonal is all 1 and every non-diagonal element is a 0. And here's the special property that it has. Let's go ahead and do a little bit of matrix multiplication. Let's say that I have a matrix which has the elements A, B, C, and D. And I'm going to take this, I'm going to multiply it by that identity matrix, 1, 0, 0, 1. When we do this multiplication, right, it's rows by columns, row by column. And so when we generate out our product matrix over here, we get a pretty simple outcome. It's going to be A times 1 and B times 0. The next entry is going to be A times 0 and B times 1. It's going to be C times 1 and D times 0. And then finally, it's going to be C times 0 and D times 1. What do you notice here?
It,
The same.
it didn't change anything, yeah.
It returns back the exact same matrix that we had on the left-hand side here, right? So what this is telling us is that if this initial matrix is A, and we take matrix A and we multiply that then by the identity matrix, it always just returns back that original matrix. Which, if you think about it, you've known this since kindergarten. It's just that you were only dealing with matrices which were 1 by 1. What happens if you take a number and you multiply it by the number 1? What does it always produce?
That same number.
Right, it just spits back that original number.
Yep.
7 times 1 is just 7, and we use that trick all the time when it comes to manipulating fractions. The number 1 exists in any size matrix. This is just the original one you were taught, but that exact same logic applies no matter how big the identity matrix is. This is the main thing that it does. So we'll go ahead and write that down in words. So any matrix multiplied by an identity matrix, which again is the special place in mathematics for the capital letter I. So whenever you see a capital I in math, universally it means identity matrix. Any matrix multiplied by an identity matrix returns back that original matrix. And here's why we care about this. Producing an identity matrix is the final goal of Gaussian elimination. Let me show you what I am talking about. Can I move this page of notes? Is that okay?
Yeah.
Okay. Okay. So here is the procedure of Gaussian elimination. What Gaussian elimination does is it assists us in solving a system of linear equations. It's going to give us the exact same answer to all those questions we were dealing with in section 1 and 2 at the beginning of the chapter. The question, where does this line cross this other line? Except this procedure allows us to solve those types of questions in a very organized way, which is useful in solving higher dimension systems. Gaussian elimination. Gaussian elimination. I'll just write the procedure out first, like in words, so that you can follow it along when you do your homework. In case you have, give me 1 second. In case you have, okay. I'm sorry, I lost my train of thought. I'm going to write it out in words first so that you can follow along with it as you do your homework, but of course, we'll do an example down below. The first thing that you're going to do is you are going to take your linear system and you are going to rewrite it as a coefficient matrix. I'm sorry, an augmented coefficient matrix. Then you are going to perform row operations, which the row operations are actually exactly the same as they are when we do the process of elimination. When we're doing elimination, in order to solve a system of linear equations, there are only 2 things that you can do. You can multiply the entire equation by a number if you're trying to line up 2 of your variables so that they cancel. And the other thing that you can do is you can take one equation and you can add it to another equation. In an identical fashion, here are our acceptable row operations. We can multiply a row by a constant. We can multiply a row by a constant. or we can add one row to another. These are the only two operations that you have to do in order to do Gaussian elimination. And our goal in doing these row operations is we do row operations until the left-hand side, which I'm going to shorten to LHS. A lot of the times, if you're talking about sides of an equation, LHS, left-hand side, RHS, right-hand side, until the left-hand side is an identity matrix. Now, when you are working towards turning your left-hand side of your augmented matrix into an identity matrix, you're going to go through a couple different phases as you do it correctly. And so when we have our original augmented matrix, we're going to have, and I'm just going to use a 3x3 here for the sake of this example. You may have some A11, A12, A13, A21, A22, A23, A31, A32, A33. The first thing that you want to target is you want to target eliminating the numbers in the bottom left-hand corner. So the first things that you want to try and delete by row operation are these guys. You want to get rid of those first. And if you succeed in doing that, you will produce a new matrix, which only has the following entries, A11, because you'll zero out these three, A22, A33, A12, A13, A23. Right? So one way of talking about this is to say that all of the elements below the diagonal have become zeros. And when a matrix is in this form, this has a name. This is called being in row-echelon form. Just a name for a matrix of this shape if everything below the diagonal is zeros. And then if you keep working at this, once you have it in row-echelon form, now you want to target eliminating the values up above the diagonal. So the next three things to destroy are those guys. And if you were to do that, you would get a diagonal matrix. A11, 0, 0, 0, A22, A33, 0, 0, 0. Once you have a matrix in this form, this is called reduced row echelon form. And reduced row echelon form is only one step away from being an identity matrix. All that we would have to do to turn this guy into an identity matrix is multiply row 1 by 1 divided by whatever this number is, multiply row 2 by 1 divided by whatever this number is, multiply row 3 by 1 divided by whatever this number is. And once you have done that, once you have turned it into the identity matrix, number 3, once the left-hand side, I'm sorry, let me use the capital letters here. I like broke this. It's not supposed to do that. So now using it is really hard. Oh, and I got it. Okay, sorry. Once the left-hand side has an identity matrix, then the right-hand side is the solution to your system of equations. And why this is actually kind of complicated, but we're going to do a really quick example, and I think that will help us see why it is the case that once we do this, the right-hand side must necessarily be the solution. Are there any questions on this little outline of the technique? No, okay. So for example, let's go ahead and say that I have the following system of linear equations that I want to solve by Gaussian elimination. I have 2x plus 3y is equal to 6, and I have that x minus y is equal to 1/2. And I want to know where x and y cross each other. Is this okay?
Yeah.
This is okay. Okay. So the first thing that I'm going to do is I'm going to turn this into an augmented coefficient matrix. And here's what that means. Here's what that looks like. All I'm going to do is I'm going to pull the coefficients off of here, 2 and 3 and 1 and -1, 2 and 3 and 1 and -1. I'm going to pull them out. That is my coefficient matrix. Here's what makes this an augmented coefficient matrix. I'm going to say that if I were to take this guy and I were to multiply it by a matrix, which is a 2×1 xy, this would be equal to a 2×1 matrix, 6 1/2. Now go ahead and look at the logic here. If you were to literally do the matrix multiplication of this times this, you would just get back these top two equations. This first row would say 2 times x plus 3 times y is 6. And then the second row would be the same as saying x times 1 and y times -1 is equal to 1/2, which would give us back this right here. Is it okay how this set of matrices is literally identical to this set of linear equations?
Mr. Robinson, how would you know to put the x or y on top, like on the first row or second row?
If you were to swap the rows, it would be irrelevant. It would be exactly the same.
Oh, okay.
Mm-hmm.
Oh yeah, I see it. Okay.
Yeah, good. Okay, so and just for the sake of talking about these bits and pieces, I'm going to say that this thing here is A, this thing here is matrix, typically we call it capital X, which I know doesn't look great because of this letter X here. So I'm going to add a couple little serifs on it just so that we recognize it's not the same X as X, the variable. This is matrix X, the 2×1 made of X, Y. And then over here on the right, we'll say that this is B. Yeah. And so all that we have to do in order to solve out this matrix is we're just going to remove matrix X for our considerations as we move forward. So here is the matrix that we're playing with. 2, 3, 1, -1. And then to keep it separate over here on the right, 6, 1/2. And now all I'm going to do is I'm going to do the procedure of elimination. And until the left-hand side is an identity matrix. And so I'm going to start off by targeting this guy, just like I said in that intro. The bottom left corner is what we want to get rid of first. So if I want to eliminate 2 with 1, what does this number need to be equal to so that it adds up to 0?
-1.
We would need this to be -2, so that when I add 2 to it, the sum is 0. So to make this position in the matrix -2, I'm going to multiply all of row 2 by -2. So here's what that turns our matrix into. It's going to be 2, 3, 6. And then if I multiply row 2 by -2, it becomes -2, +2, -1. We only have 2 eligible row operations when it comes to manipulating matrices. You can multiply a row by a number, and you can add 1 row to another. Those are all the operations that we're going to have to do here in order to get our answer. So now that these two are equal in magnitude but opposite in sign, I can now add row 1 to row 2. And this is my own little nomenclature here where I'm writing on the outside what I'm doing with each step. You can take that or leave it. I just think it makes it easier if you were to make a mistake at some future step to go back and look at what exactly you had done. It's really easy for this kind of work to get messy. So here's how I keep track of the fact that I'm adding to this row 1. I usually just use a Roman numeral just to keep note of that. So I'm going to add row 1 to row 2. And that is not going to affect row 1 at all. Row 1 is still 2, 3, 6. But that will affect row 2. So 2 plus -2, well, that's 0. That's great. 3 plus 2 is 5. 6 plus -1 is also 5. Is that okay?
Yep.
Okay.
Yes.
And now, like I said before, this is now in row echelon form, that bottom left corner is 0. However, we're not done until this left-hand side is the identity matrix, which is to say we now need to aim for reduced row echelon form. So our next target is this 3 up here, this 3 up here in the top right corner. So if I want to eliminate this 3, what does this need to become? You can only eliminate positive 3 with
-3.
-3.
But Mr. Robinson, aren't you trying to eliminate 3?
I am trying to eliminate 3.
So could you multiply the first row to actually no.
Okay, I'm going to multiply this bottom row to make this digit -3. And to do that, I'm going to multiply that bottom row by -3/5. The point of that is so that 5 cancels with 5. 5 over 5 is 1. And then it just makes this entry here -3. So here's what our matrix becomes, 2, 3, 6. And if I multiply that bottom row by -3/5, -3/5 times 0, well, that's great. That's 0. That's why we want to try and bottom out or zero out the bottom left corner first, so that we can manipulate the bottom row without it changing any of the values. And then this becomes -3. And 5 times -3 over 5 makes this also -3. Now that I've lined these up for elimination, I'm going to go ahead and I'm going to add row 2 to row 1. So plus row 2. And so that's not going to change our bottom row at all. Our bottom row is still going to be 0, -3, -3. But what does our top row become? So it's going to be 0 plus 2. That's still 2. It's going to be -3 plus 3. That's now 0. And it's going to be -3 plus 6. That's now +3. The final step is that I am now going to turn the left-hand side into an identity matrix. So what do I need to multiply row 1 by?
A 3.
I need to multiply row 1 by 1/2. What do I need to multiply row 2 by? I now need to multiply row 2 by -1/3. So the point of this is so that the left-hand side will become the identity matrix. So 1/2 times 2 will give me back 1. -1/3 times -3 will also give me back 1. And so when I do this, it's going to give me 1, 0, 0, 1. And then on the right-hand side, 3 divided by 2 is just 3/2. And -1 over 3 times -3 is going to give me back +1. And now here's what this tells me. This is my answer. So the answer to the question, hey, I have this system of linear equations, these two lines, where do they cross? The answer must necessarily be 3/2, 1. Are there any questions on what steps it is I have to take in order to get this correct answer?
Mr. Robinson, why did you add the first row to the second row like the first time, and then the second time you added the second row to the first? Like, what's the difference?
So you could do it in a reverse order. You could eliminate the values in the top right-hand corner first. But when you are eliminating a value, you can only eliminate it with other values in the exact same column. So here, the only way to make this go to 0 is to hit it against whatever this number is. The only way to make this go to 0 is to hit it against whatever other values are in its same column. Okay, and here's why this works. Here's why this is true. We started off with a setup that said this matrix A multiplied by this matrix X is equal to this matrix B. This is the matrix version of this system of linear equations. all of these row operations, they don't actually change the value of x. Notice all of those operations were done after I removed x from being present here at all. So once we get down here, because these row operations don't actually affect the internal values of a matrix, they don't change its solutions. Once we get to that bottom position, here's what we're saying. 1, 0, 0, 1, then multiplied by that matrix X, which was made of the entries X and Y, is equal to this other matrix here off to the side, 3/2 and 1. And what's the rule about something getting multiplied by the identity matrix? What does it yield?
That same matrix.
It just gives back that exact same matrix. So this times xy is telling us that, well, x times 1 plus y times 0, that's x. X times 0 plus y times 1, well, that's y. Well, this set of ordered pairs, xy, is equal to 3/2, 1. That's why this technique works. We're manipulating the left-hand side until it is the identity matrix. Once the left-hand side is the identity matrix, because it is being multiplied by our variable matrix, whatever is on the right-hand side has become the answer. This technique is identical for matrices of any dimension. And tomorrow when we come in, we are going to start off by doing this exact same procedure for a 3x3. Like I said, it is exactly the same. It's just a little bit more time consuming. And I'm sure a bunch of y'all are thinking like, hey, why would I bother with this when substitution works? Yeah, substitution will give you the exact same answer, and substitution might be faster for a 2x2, but I assert that for any other size matrix, once you're talking about a linear system of 3 equations, or even more fun, a linear system of 4 equations, which means that you're not solving for XYZ, you're solving for WXYZ, you will be begging for a matrix. It makes it way easier and more organized. It makes it harder to lose values. This is a superior technique in all of those cases. So, yeah.
Mr. Robinson, I feel like it's very similar though, like how you try to equal out x and y, or not equal out, cancel out the x's and then the y's. I don't see the difference really.
There isn't a difference. It's literally identical to the steps taken during elimination.
Right. Oh,
Yep.
okay.
It's a lot less writing.
It's more organized.
It's
I
a lot
guess.
more organized, and we'll find it's a lot more versatile, especially for
okay.
dealing with 4x4s.
Yeah. Okay.
Yeah. I was gonna write down a 3x3. We definitely don't have the time to run through it right now, so we'll just do that for tomorrow's warm-up. I'll post the homework now so that you can get started on it if you'd like, but it probably won't be due until Saturday night. You all have a nice day, and I'll talk to you tomorrow morning.
Thank you, Mr.
Yep. Thank you, Mr. Robinson. See you.
Peace.
Bye, Mr. Robinson.